Alrighty, so our goal for today, last time we had class, we sort of set it all up, right? We gave you some perspectives on radiation, what radiation is, where it comes from. We talked a little about radioactivity. Today, we're going to try to get you the units for radiation, how we measure radiation, so the units that we use to measure radiation, and then the devices that we use to actually measure radiation with. So we're going to focus on radiation units and measurement. I think it's worthwhile to put up on the board the units that we're going to be looking at, and what they sort of mean. So let me get a couple of things up here. So So these are the four ways that we're going to be able to measure, that we're going to talk about measuring radiation. We're going to talk about exposure, absorbed dose, dose equivalent, and effective dose. These are the four things we're going to talk about that are measured today, and these all are going to have their own individual units. And what I'm going to focus on are the SI units, the System International, the metric units that we use, right? So we don't focus so much on the standard units anymore, they're standard or British units. We're going to focus on SI units. I will give you some of the stuff for those standard units, but let's go ahead and talk about these things. So for exposure and absorbed dose actually use the same unit. That unit is the gray. And we're going to talk about these in a minute here, but I'm just going to get the names for them out, okay? Now, exposure, as we're going to learn in a few minutes here, exposure has to do with intensity of radiation before it interacts with, like, the body, the thing that we're exposing, right? So exposure is how much you're exposed to, not how much gets into you, okay? So for us, exposure is going to be a measurement taken in the air, from the air, not within the body. So the abbreviation for this is capital G, little y, and then with a subscript of A, A, okay? So subscript A means gray in the air. Gray is an amount of radiation. We'll talk about that in a little bit. And then gray with a subscript A means air, so exposure. It's the same for absorbed dose. We still use the unit gray, but our subscript becomes a T. So gray sub T, that's T stands for tissue. So it's absorbed dose into tissue. Good morning. Now, for dose equivalent and effective dose, these both use a unit called the sievert. Okay, so really we're working with two simple units today, sieverts and gray. These are names for amounts of radiation, kind of like the foot and the inch, right? So we're going to talk about these. We're going to talk about what they mean, how much each one is worth, like what is 1 gray worth of exposure, right? What can that do? Right? We learned a little bit about that last time. So that's our plan here. So we're going to sort of get a little more complicated as we go into this. Hopefully everyone got the notes. I actually sent this chapter's notes out with the original email. Okay, so you got 39 and 40 all at once, so this should be in that original email I sent y'all. So that's the first thing we're going to do. We're talking about radiation units. Again, we think about like the foot, the inch, the liter, right? These are all units of measurement, and we have units of measurement for radiation. So just to kind of restate this, the SI system, System International, right, is the worldwide standard of measurement in science and medicine. Medicine's a branch of science, so just think science, okay? We use the metric system, okay? So we measure things by, we measure weight by the gram, and we measure liquid volume by the liter, right? We measure radiation with the gray and the sievert, okay? These are our units that we're going to be exposed to. So we have things like, and I just put these 4 on the board, right? 4 basic quantities measured: exposure, dose, dose equivalent, and effective dose. These basically go in increasing detail, right? Radiation exposure will tell you how much radiation is in the air above you, right? How much radiation you can be exposed to. Dose will tell you how much actually absorbed into your body. Dose equivalent will tell you how much was absorbed into your body from the exposure and relate it to the harmfulness of that radiation. So it'll indicate some kind of biologic harm. Okay. For example, you guys learned last time, what are the different types of radiation that we deal with? We have like 3 different categories, 2 broad categories, right? We have particles and we have waves, right? In the particle category, what are those 2 particulate types of radiation? Alpha and beta particles, right? Alpha particles were big and heavy, beta particles were small, right? Both of them cause biologic harm that was greater than X-rays, which are a wave type of radiation, right? X and gamma rays, waves; alpha and beta particles, particles. They do different amounts of harm. If I exposed you to 1 gray of X-rays and then exposed the person next to you to 1 gray of alpha particles, the person exposed to 1 gray of alpha particles gets a lot more harm. Okay, we can quantify how much more harm by using these units. Okay, dose equivalent will let us do that. Effective dose takes the first 3 into account. So you notice each one is taking the previous one into account, right? Exposure is taken into account with dose. You need to be exposed to radiation before you receive a dose of it, right? Once you receive a dose of it, if you tell me what kind of radiation it is, I can tell you how harmful it was. Once you know how much you were exposed to, how much was absorbed, and how harmful that radiation was, with effective dose, you can use those prior 3 things and add on the type of body tissue that it was going into, okay, to indicate the total amount of harm caused, okay? So effective dose takes into account how much was absorbed into you, what type of radiation it was, and what tissues of the body were being exposed, okay? Just to give you sort of a flavor for that right now, a good example of sensitive body tissues are your gonads, ovaries and testes, okay? A good example of radio-resistant, non-sensitive body tissues is your nervous system, your brain and spinal cord, okay? Very, very radio-resistant, okay? So you've got different levels of tissue sensitivity in your body. Those tissues can be exposed to different types of radiation and in different quantities. That's the purpose for having these 4 different ways of expressing how much. So that's what we're going to work with. In this bottom right picture here, we have a measurement device called the Geiger counter or Geiger-Müller tube. I'll bring ours out in a little bit, and we're going to talk about these a little bit today. Okay, so let's go ahead and jump into this. I have a lot of things to talk about. All right, so we're going to start off with the easiest one first. That's exposure. Okay, I'll read the definition, then we'll try to maybe break it down a little bit. So the definition is the intensity of radiation incident upon the surface of an object. Let's start off with the first part of that. What do they mean by intensity? Yeah, how much, right? If we're talking about intensity of light, if I made a light more intense, what have I done to the light? Made it brighter, right? Not necessarily stronger, because that would be like changing the color, right? You made it brighter, though. You took a flashlight and you doubled its brightness. You doubled the intensity of the light, yeah? Okay, and you can see that like at nighttime. If you have a very dim flashlight, that dim light bounces off of everything and you can't see very much, right? You have a very bright flashlight with more intensity, then it bounces a lot of light off of things, and then all of a sudden it's bright at night, right? Like your headlights are on your car. Okay. So it's the intensity of something. That's the intensity of radiation, okay? Radiation, we learned, is a form of energy. This form of energy comes in particles moving fast or waves moving fast, okay? But radiation is a form of energy. So it's the amount, intensity, of radiation incident upon the surface of an object. Just incident just means it's there, like it is there, like It's just above the surface of the object, right? It is interacting with the object. The surface means for the skin, it's just the level of the skin, right? And the object is a person usually, okay? The object could also be a volume of air in the room, okay? It's the amount of radiation hitting a thing. That's what exposure is. So notice it says nothing about how much actually absorbed into the patient, what type of radiation it was, and what type of tissues it's interacting with, right? We're not even saying it's interacting with anything yet. We're just saying there's an amount of radiation that could interact with an object, okay? Now the way this is measured is by detecting ionization events in the air above the object, okay? There's air above all of the objects, above and around all objects, right? At least in our atmosphere here. And if we send like an X-ray beam through the air, it's going to interact with the air, okay? And you guys learned in the previous lecture that the X-ray beam can strike the small little atomic particles, the atoms that we're made of, and the atoms that the air is made of, and it can ionize them, right? It can break those atoms apart, okay? So oxygen and nitrogen in the air and similar particles in your body can be broken apart. The air can be ionized, and we can measure that amount of ionization in the air. You can actually detect it as an electric charge in the air, okay? Good. So we can measure the amount of ionization, the amount of charged particles created in the air as an X-ray beam interacts with some volume of air. And by doing that, we can tell how much radiation there was. Okay. So ionization events in the air above the object. Those ionization events can generate an electric charge in a device, okay, in a radiation detecting device. So we talk about entrance skin exposure, which is just that. It's just exposure, but just given a new name, entrance skin exposure, the intensity of radiation entering through the surface into the body. So it's how much radiation the body is going to be exposed to is their entrance skin exposure. Okay, this is what radiation, like when you look at exposure for an exam, like you look at the average exposure for some exam, they're giving you the entrance skin exposure for that exam. If they're saying some exam exposes somebody to 1 milligray or something like that, that person was exposed to 1 milligray above their body, right? The radiation interacts with the air above the body, creates an amount of charge equivalent to 1 milligray, and that's how much radiation can actually interact with the body. It doesn't mean that's how much will absorb into the body. We'll look at that in just a little bit here, but we're saying that there's an amount of radiation that's going to enter the body. That's the entrance skin exposure. It's the total amount that could possibly be absorbed. Yeah.
Is this also how we measure like the exposure deviation when we take the X-rays?
In a way, so when you measure exposure deviation, the detector knows like how much it's expecting, right, and how much charge it actually gets, and it compares how much charge it received, right? So the X-rays hit the detector and it creates some electric charge. So it's comparing how much charge it expects versus how much charge was actually received, and then it gives you an amount. But it's not measuring exposure though. It's measuring more like an absorbed dose kind of thing. It's a little different. Yeah, but it's a similar idea. Yeah. The way it measures it is different, but what it's expressing to you is its exposure, entrance skin exposure, but not in those units. Yeah. So it's not a good way to, like, when you see exposure deviation on the computers, right? It's not telling you how much they were exposed to. It's just telling you of what it expected them to be exposed to. Here's the relative percentage, right? So you either got exactly the right amount, a little more, a little less, but it's not telling you exactly how much. Qualitative, not quantitative.
And that's calculated by what's hitting the IR?
Yeah, it's calculated by what the IR expects to receive for that exposure and how much it actually receives. Right, and the difference between what it expects and what it actually gets. Like it could get more, it could get less, or it could get the exact right amount. And and what it's actually doing is measuring an amount of electric charge created when the X-ray beam strikes the receptor. But it can't measure entrance skin exposure actually because the measurement's actually taken at the detector below the body. So we would only be able to do that if we had some detector above the body. That's why it's different. It uses the same word, exposure, though. That's the problem. Okay. All right. So yeah, when you think about being exposed to something, if you're exposed to something, that something didn't come from inside of you, right? So we're thinking an amount of radiation coming from the outside world, right? We speak of being exposed to things from the outside. We said radiation is defined as the intensity of radiation incident upon the surface of a body. That is, be it a human body or an ion chamber. An ion chamber is like a detecting device. You can't count the number of photons that are in the air that are in the X-ray beam. All you can do is you can make an X-ray beam and you can count the amount of electric charge created in the air when the X-ray beam passes through it. That's what you can do, okay? You can put a detecting device in the way of the X-ray beam and have that detecting device get ionized when the X-ray beam interacts with it. The way this works is when the X-ray beam strikes the air molecules or strikes the gas chamber inside of a detecting device, okay, it will liberate air molecules. It will free them. It will ionize the air or ionize the gas inside of the detecting chamber. When you ionize gas or air, you're freeing electrons. You're causing electrons to hop off of the atoms in the air or the gas, okay? And those freed electrons can generate an electric current. We can measure that electric current. That's the idea. We're taking an amount of exposure in the air or in a little gas chamber that we use to detect things, and we're letting an amount of radiation pass through it, create some amount of electric charge, and we can measure how much electric charge was created and infer from that how much radiation exposure there actually was. Okay, so now the unit for exposure, okay? The unit for exposure is called the Coulomb per kilogram. A Coulomb, remember what did I just say we're doing, right? I said we're measuring an amount of electric charge created in the air when radiation happens to the air or the gas inside of a detecting device, okay? But importantly, what did I say? We're measuring an amount of electric charge, okay? The Coulomb is a unit of electric charge. Okay, so the Coulomb per kilogram as a unit is saying how much electric charge is created per kilogram of matter. Okay, so you probably know this, but you may not know it like this, right? Or at least before you read the chapter, you didn't know it in this way. But you know the atmosphere weighs something, okay? It's got some weight to it. If you put something in the atmosphere, in the air in the room that's heavier than the air in the room, such as yourself, you will sink to the bottom of our atmosphere, right? If you put something in the atmosphere that is lighter than the atmosphere, it will float, okay? Like a helium balloon does, okay? The atmosphere has some weight to it, okay? And interestingly, it's actually quite a bit. 1 cubic meter of air, so if you just imagine a box 3 feet by 3 feet by 3 feet, okay, that cubic meter box that I'm holding right now weighs 1 kilogram, okay, 2.2 pounds, okay. So in every meter cube box of air, of air in the room, you've got about 2.2 pounds of matter, okay. So if there is 1 Coulomb per kilogram within exposed to that meter, that cubic meter, okay, you've created 1 Coulomb of charge, 1 Coulomb of electric charge within that box, okay? That would be 1 Coulomb per kilogram, okay? It's an amount of electricity, okay? Remember, the Coulomb is an amount of electricity. It's, 6.3 times 10 to the 18 electrons liberated, okay? If this were an electric circuit, 1 Coulomb of electric charge would be 1 amp moving through the circuit. So if you've been with me for long enough, you've heard about the amp, right? It's 1 amp moving through an electric circuit, 6.3 times 10 to the 18th electrons moving. This is just a static amount of charge in the air, okay? So if you create 1 Coulomb of charge in a kilogram of air, you've made an exposure of 1 Coulomb per kilogram. Is everyone okay with that notation, 6.3 times 10 to the 18? What type of units is this? What are we expressing this in?
Electron units.
Sorry, just the number 6.3 times 10 to the 18.
Scientific.
Scientific notation, okay? So that number, just so, I know some of you said me for this before, but 6.3 times 10 to the 18, it's a way of expressing a very large number in a compact form, right? All this is saying is take the number 6.3 and multiply it by 10 to the 18th power, okay? If I just said take 6.3 and multiply it by 10, what's the answer?
63.
Yeah, did you need to do a bunch of complicated math? 'Cause I saw a bunch of people going and like numbers, shooting up above their head, little thought bubbles going up above their heads, right? It's not hard, right? Because you know anything multiplied by 10, what are you going to do with the decimal point?
Just move it over.
Move it over one place to the
Right.
right, okay? So 6.3 times 10 is 63, okay? You know that anything multiplied by 100, then, do you have to do a lot of thought with that? So what's the answer?
2 points, so it's 630.
630. And all that's happened here is the decimal point went 1, 2 spaces over to the right, okay? What's the answer to that? Right, so just it is just that simple, right? Anything multiplied by 10 is that number with the decimal point shifted over to the right, and every increasing multiple of 10 shifts the decimal point another place over, okay? Well, 10 is secretly 10 to the first power, okay? 100 is secretly 10 to the second power, and 1,000 is secretly 10 to the third power, okay? I could keep going, right? So 10,000 is 10 to the fourth power, and you get the idea, right? Okay, so it keeps going, okay? 10 to the 18th power just says take the number you're working with and shift the decimal point over 18 places, okay? So it's a number with 17 zeros, right? 17 zeros after that 3. It's a very large number. It would take us a long time to put that very large number on paper, do any calculations with it, but when we shrink it up and put it into scientific notation, then we can, you know, have a lot easier time with this. So if I gave you the number like 4,500,000, right? That's 500,000.0. Okay, so you see the decimal point. You can just put that into scientific notation pretty quickly, yeah? So take a second, try to put that number into scientific notation, and tell me what you get.
4.5 times 10 to the 6th,
Let's see.
I think.
1,
I might be off.
2, 3, 4, 5, 6. Why did you stop there? You're right, but why did you stop there? Why didn't you make it like 0.45 times 10 to the 7th?
Some obscure rule that I don't remember the answer
The
to.
rule is it's not obscure, it's just you gotta remember it. It's
Yeah.
just move the decimal point till you're to the right of the first non-zero digit, okay?
That's it.
Okay. The first non-zero digit is that one. Going from the left. Okay, anyways. But that is it, 4.5 times 10 to the 6th. 4.5 times 10 to the 6th. Okay, those two things are equivalent to each other, okay? All right, all of that just so you can make sure you've got what we mean by that. That's just a big, big number. Put into words, it is about 6 billion ionizations in the air. Okay, so 1 coulomb of charge is 6 billion ionizations. Okay, you make that much charge from an amount of radiation in a cubic meter of air, you've created 1 coulomb per kilogram of exposure. If you doubled that, well, then you made 2 coulomb per kilogram of exposure, okay? If you made half that, you made a half of a coulomb per kilogram. That's the idea, okay? So it's an amount of electric charge generated in air based on an amount of radiation exposure. This is the way we express it. All right. By the way, this is that when I stated cubic meter of air like they show here, weighing 2.2 pounds or 1 kilogram, that's at typical atmospheric pressure. If we climbed to the top of Mount Everest, okay, and we took a cubic meter of air, would it weigh more or less?
Less.
Less. And why?
The air's thinner up there.
thinner up there. Yeah, you know that because when they go climb Mount Everest, they got to go take like oxygen masks and stuff, and people die up there, right? And part of it is because of the lack of oxygen. Okay, so good. If we were, you know, we're here. We're not exactly at sea level, right? We're close-ish, but we're a few hundred feet, I think, above sea level right here. And if we went exactly to sea level, you go to the beach and take a cubic meter of air. Is it going to weigh more or less than our cubic meter of air here? More, right? Because you're getting closer to sea level. The closer you get to sea level, the further you get towards the bottom of our atmosphere. Okay, so atmosphere has a pressure. The closer you get to the bottom of it, the more pressure there is, the denser the air is. Okay. As well, if it's a very cold day, this is not that important, but just to give you some reference. If it's a very cold day, the air is denser. Okay, if it's a very hot day, the air is less dense. The air is expanded. Okay, so anyways, that's stuff to think about. But anyways, 1 coulomb per kilogram would generate that much charge in a cubic meter of air. Now we're not going to, in a little bit here, we're going to talk about absorbed dose. So we're going to have to equate what's a kilogram in the body. Okay, the body's a lot denser than air. Okay, so the volume of body that is going to weigh 1 kilogram is going to be much, much smaller than the amount of air that would weigh 1 kilogram. We'll get there. Okay, so coulomb per kilogram, and often it's called air kerma. Okay, so exposure given the unit of coulomb per kilogram is often referred to as air kerma. Kerma is not someone's name this time. Okay, does anyone remember reading this from the textbook? What's kerma? Kerma stands for something. It's an acronym. It stands for kinetic energy released per mass, per amount of mass. Okay, basically it's coulomb per kilogram. Okay, it's just another way of saying it, air kerma. So if you see air kerma, they're talking about exposure. Okay, quantity air kerma has largely replaced the quantity exposure for expressing intensity of the raw X-ray beam, and that's just it, right? Air kerma is the same as exposure. Okay, now 1 coulomb per kilogram would be 1 gray worth of air kerma. So the gray is a coulomb per kilogram. So the unit I just gave you, this previous unit, coulomb per kilogram, is the gray. Okay, so if some amount of air, right, gets 1 coulomb of charge, one cubic meter of air receives 1 coulomb of electric charge, that cubic meter of air has been exposed to 1 gray of radiation. And we would use the subscript A if we're talking about the exposure in the air. We haven't gotten to the body yet. We will get to the body. Okay. Now, we do talk about exposure, but we talk about exposure in the context of how much of that will actually be absorbed by the body. So what really matters, right? Exposure matters because that tells you how much, what's the total possible amount of radiation somebody could receive, right? They can't receive more radiation than they were exposed to, okay? But if you're exposed to an amount of radiation, you may not absorb all of it, okay? As you learned, the X-ray beam passes through the body, right? And exits the body, some of it, and hits the image receptor. That means that the body can't absorb all of the X-ray beam, okay? Now, there are other types of radiation, like particulate radiation, that the body can absorb all of, okay? But the idea is you're exposed to an amount, you don't absorb that entire amount. You absorb close to it, but not the entire amount, okay? But importantly, you cannot absorb more radiation than you were exposed to, right? You can only absorb as much as you were exposed to or less. So when we get to next talking about absorbed dose, okay, if we're talking about particles, it's different, but with waves like X-rays and gamma rays, some X-rays penetrate all the way through the body without interacting with the tissue atoms. Now, how would an X-ray beam made of a bunch of X-ray photons, how would that beam get through the body without interacting with anything? Like, I feel like I'm pretty dense. I feel like it's kind of hard to like pass through me without interacting with my body tissue. So how can the X-ray beam get through the body without interacting with it? How can any of the X-ray beam get through the body without interacting with it?
It has a higher energy.
Well, nothing to do with energy yet. Think about the body, right?
Absorb through the body?
Yeah. So it goes. There's some amount of exposure come in this direction towards the body. It ionizes the air and then hits the body, right? Whatever hits the body can be absorbed into the body, but some of it's going to pass through. Some of the X-ray beam is going to pass through the body with zero interaction. Okay, how is that possible for the X-ray beam to not interact with my body?
It has too much energy.
I think you guys are thinking about KV and like penetration right now. Don't think about that. Ignore that right now. Think about the properties of X-rays. You learned that X-rays travel in straight lines at speed of light. They have no mass, okay? And they have, this is the important part, they have no electric charge, okay? The fact that the X-ray beam has no electric charge means that it is not pushed or pulled towards any of your body's atoms, okay? It can change the state of your body's atoms if it happens to hit them. It can ionize your body's atoms, but it doesn't have to interact with your body's atoms, okay? It can pass, an X-ray photon can pass through your body without interacting with it at all, okay? So that's one part of the story. The X-ray beam has no electric charge, okay? If it did have an electric charge, you could deflect it and do all kinds of fun things with it, but you can't, okay? The X-ray beam just goes in a direction.
Is that because we're like mostly made of like empty space?
That's what I was going to get to next, right? So do you know? Let's use that, right? So you're saying we're mostly made of empty space. Can you? Because I mean, like some people might be thinking, like, okay, that like my chest cavity full of air, that feels like empty space. But what are you actually saying?
Like the space between an atom, like where the nucleus is compared to where the electron is.
Yeah, right. You have an atom, right? An atom made of a dense nucleus and orbiting electrons, and there's a lot of space there, okay, between the orbiting electrons and where the nucleus is, right? If that's the nucleus of an atom, right, like that, the nearest orbiting electron will be about a football field away, okay? So if we blew up a nucleus of an atom, a single atom, to the size of this, cap, okay, the orbiting electrons are going to be a football field away. Now, there's a lot of space between here and there, right? Now, shrink that down to very small atomic sizes, and there's still a lot of space between the electrons and the nucleus of the atoms. And the X-ray photon is not specifically drawn to or pushed away from the nucleus of the atom or the electrons orbiting the atom. So some X-ray photons are going to hit some atoms and some electrons, right? But some X-ray photons are just going to zoom right through that big empty space, okay? We feel the sensation of like solidity, right? Simply because of the amount of electric repulsion between us and the things we touch, right? It's mostly the electric charges interacting that give us this sense of like solidity in our bodies, right? Interestingly, the people that discovered this empty space part of this idea, it's rumored that the next morning he wakes up and he is terrified that he will fall through the stairs as he walks down them in the morning to go to his front room or whatever. Because of this, you don't think we feel solid, right? But then you learn that nothing is truly solid. There's a bunch of empty space between everything. And it's just electric charge, electric repulsion, keeping things feeling solid. Like when I hit this table, I'm not actually touching the table, right? It's electric charges between my hand and the table interacting. We're not actually touching, okay? Good. So X-rays, so that's all to say, X-rays can penetrate through the body without touching anything, without interacting with it. That means an amount of exposure, right? Some of that won't be absorbed within the body, okay? Some of it will, a good majority of it will, okay? So we're about to learn that, a great majority of it does. But so let's keep going. Okay. So the analogy is to compare it to like medicine, okay? So for a dose of medication is given to the body, right? So you expose somebody to some medication, right? Here it is. You have them ingest it, and they absorb some of it, right? And it is true with medication that whatever you give them is not what actually absorbs into the body. Okay, you may know that like your liver, for example, if you take Tylenol, take 1,000 milligrams of Tylenol, your body's not going to have 1,000 milligrams of Tylenol acting on it. It's going to have less than that because your liver is going to detoxify some of it, and over some time, your liver is going to work all of that Tylenol out of your body. Okay, which is why 6 or 8 hours later, you're going to take more Tylenol. Okay, because it's being worked out of your body. But the point is that if you expose yourself to some amount of medication, it will not all be absorbed within your body. You will not receive the entire dose that you were exposed to. We don't use terms like that really, but it works the same with radiation, right? You're exposed to some amount, you won't absorb it all. Okay, so absorbed dose will be a little bit different than exposure. The unit for measuring absorbed dose, or the concentration of radiant energy deposited within a body tissue, is the gray. So we're seeing the gray showing up again. Okay. So the gray is used as a unit for exposure, gray for the air, an amount of exposure in the air. It's also used as a unit for absorbed dose. And this is where we really use it more often, is talking about absorbed dose. So we'll say the patient received some amount, usually expressed in milligrays or micrograys, right? Milligray would be 1,000th of a gray. Micrograys are millionths of a gray. And so large unit, fractional units, milligray, little m, big G, little y. Microgray, this unit, GY, right? So micro, this little symbol means micro or millionth, okay? All right, so the gray, a new unit of energy, okay? So remember the Coulomb was an amount of electric charge, okay? The joule is an amount of energy. Okay, so the joule, we'll talk when we get back to when we circle back around to physics and talk a little bit more about electricity, electrodynamics. We'll talk more about the joule again, but the joule is an amount of energy. So it's not an amount of electric charge. You can express electric charge in units of joules. Okay, so for example, the very common one is with AEDs. Okay, an AED shocks somebody, uses electricity to shock somebody. We say how much electricity it's delivering by expressing that in units of joules. Like an AED will administer like 300 joules of energy to somebody, okay, when they're shocked. But a joule is an amount of energy, okay? It's this nice convertible amount of energy. It can be used to talk about electricity. It can be, let me rephrase that. The joule can be used to express all different forms of energy, okay? So we like it for talking about energy. Energy, well, what's the simple definition of what energy is? There's a few ways to define energy, but what do you guys think of when you think energy? What are you thinking? Because I have like a one sentence thing that I think when I hear energy.
Well, what I know is
See what Michael says. Let's see what Michael says first, and then I'll give Lewis a chance.
the ability to do work.
Yeah, that's my little one sentence phrase that sits in the back of my head, right? The ability to do work. Lewis, what are you thinking?
I was gonna say like conversions between like states of mass.
Right, so you're thinking like energy is conserved, something like that, or it is the thing that sticks around when there's different interactions, right? Like for example, when I have my hand and I hit this table, right? I put energy into the table, right? I did some work to the table. I converted the energy of my hand moving into some sound and heat, right? So I put work into the table. It's the ability to do work in some aspects. Some ways to think about it include the ability to do work. Okay. Another way to think about energy, it's just the thing that's conserved between interactions. Okay. I put some energy into a baseball that I throw. The baseball now has that kinetic energy, and the baseball hits the wall and converts that energy into other forms. Right. You hear the sound hit your ears. Right. Energy is converting into other forms. It hits your ears, works down your ear canal, gets to your brain, converts into electricity. The point is that energy can convert but is always conserved, right? I'm not making energy or creating it from nothing. Joules, the joule is an amount of energy, and you can use the joule to track how much energy is moving through some system. 1 gray is 1 joule per kilogram. You're not even going to have to worry too much about that, right? Because we're just going to express things in units of gray, okay? We're going to say this exposure gives somebody this much gray, this other exam gives somebody this much gray, right? Here's how much gray can cause harm. That's all we're going to have to do is just talk about it in units of gray, okay? The gray is that unit for kerma, kinetic energy released per mass, okay? And the gray subscript A, energy in air, gray subscript T, energy in tissue. Those are our 2 units. Exposure for gray subscript A, and absorbed dose gray with the subscript of T. Okay, I want to focus on this note here. Okay. 1 gray of exposure in the air, 1 gray of air kerma, and 1 gray of tissue kerma are both defined as 1 joule per kilogram. 1 kilogram of air is about the same as 1 kilogram of tissue, okay? So basically we're talking about the same thing, right? 1 gray in the air and 1 gray in the tissue is the same amount of radiation, okay? The distinction between the two is not the mass, but the volume being implied, right? This is a larger volume. 1 gray of air kerma, just a larger volume, right? One kilogram of air takes up a cubic meter, where 1 kilogram of body tissue is about a 10 centimeter cube. Okay, so yeah, that's it right here, right? So in the body, a 10 centimeter cube weighs about 1 kilogram on average, right? They usually say take like your lower leg, for example, right? And a 10 centimeter chunk of your lower leg, right? 10 centimeters, roughly 4-ish inches, right? So roughly a 4-ish inch square, okay? That 4-ish inch square is going to weigh about 1 kilogram, 2.2 pounds, okay? So 1 gray per kilogram of body tissue is equal to 1 gray per kilogram of air. Just a bigger volume when you're talking about the air. Okay, so how to talk about these two separately or together, okay? So here's the idea. Some radiation is going to penetrate all the way through the body, okay? So as I said earlier, you can be exposed to 1 gray of radiation and you won't absorb the entire 1 gray. Some of it's going to pass through the body. Absorbed dose is always expected to be slightly less than the exposure. Okay, you can't absorb more than you're exposed to, but you can absolutely absorb as much as you're exposed to, or maybe a little bit less, and that's what's happening here. Measurements show that 1 gray of air kerma results in about 0.96 gray of tissue dose, which means you don't absorb at all. You absorb about 96% of what you're exposed to. However, 96% is pretty close to 100%, okay? So for our purposes, we get to be sort of sloppy and simple with this. 1 gray of air kerma, we're going to call that 1 gray of tissue dose, okay? So when you see an exam that says the entrance skin exposure is like 5 milligray, okay? That's going to be their absorbed dose, okay? It's going to be not exactly that, but for sloppy purposes, that's what we're going to call their absorbed dose, okay? We're going to say that whatever they're exposed to is how much they absorb, okay? So all of that precursor talk that I just gave about it's different, you can be exposed to an amount, but you always absorb a little bit less, that's going to be true always, but it's so close, whatever you're exposed to is so close to what you actually absorb that we just equate like a 1-to-1 relationship between the two, okay? So we say whatever you're exposed to is what is absorbed into you. And that's that, okay? That is how we think about absorbed dose, right? You're exposed to an amount, and that's what you absorb. Now, the gray that we just talked about for absorbed dose and exposure. That's nice, right? We get to simplify two things, right? Exposure and absorbed dose are equal for our purposes. Very nice. Okay, makes things simple for us. But it doesn't tell you much, okay? All it's telling you is here's an amount of radiation. It created an amount of charge in the air, and we can measure that. From the measured amount of charge in the air, we can say how much you absorb, okay? And what we're saying is they're equal, okay? But you can't tell how harmful that will be until you tell me what type of radiation it was, okay? Again, as we've learned, certain types of radiation are much more harmful than others. You learned last time that alpha particles are much more harmful than beta particles. Beta particles are more harmful than gamma rays. Gamma rays more harmful than X-rays, okay? So in all of the types, this is the neat thing, in all of the types of radiation that we deal with, X-rays are actually the least harmful. By we deal with, I mean in principle, like in classroom talk, right? You only actually work with X-rays in the real world. And those things that you work with, X-rays, are actually the least harmful type of radiation, okay? Gamma, beta, and alpha rays are always more energetic, stronger, more harmful. So in order to talk about an amount of actual harm that can be done by radiation, because that's what's important, right? If radiation couldn't cause any harm, then we wouldn't care, right? If alpha, beta, gamma, and X-rays all were non-ionizing, we don't care, okay? We don't need to differentiate them, right? But they all cause harm, and they all cause different amounts of harm, so we need to care about them, okay? So, to talk about biologic harm, we have to talk about this unit called the sievert, okay? The sievert is pretty straightforward. It's just take an amount of radiation in gray and then tell me what type of radiation it was that caused the exposure, okay? So you take the gray and you multiply the gray, the exposure in gray, by something called the radiation weighting factor, okay? And we just know these are given to us. They'll be given to you on the next slide, and they are in your notes. The radiation weighting factor simply compares the harmfulness of some type of radiation compared to X-rays, okay? So X-rays are the thing we're comparing against. So are X-rays going to be any more harmful than X-rays? No, right? X-rays are as harmful as X-rays are, so there's a one-to-one relationship there, okay? So you've already learned that, even before I go to the next slide, that X-rays have to have a radiation weighting factor of 1, okay? They can't be more harmful than themselves, right? They are as harmful as they are. So, okay, that'll be important in just a second. Maybe you're thinking about it right now. X-rays have a radiation weighting factor of 1, and we multiply the absorbed dose in gray by that radiation weighting factor. Anything multiplied by 1 is just, no, it's not 1.
Or it's that number.
It's that number, right? So if I take 10, multiply it by 1, it's 10, right? If I take 4.23956 and multiply that by 1, it's 4.139526, whatever I just said, right? The point is, whatever multiplied by 1 is 1, okay? That means for X-rays, the gray is the sievert, okay? However, for others, it's going to be different. X and gamma rays have a radiation weighting factor of 1. They're as harmful as they are. Again, we're comparing everything to X-rays. And gamma rays are basically the same type of thing. So they each have a radiation weighting factor of 1. Beta particles, fast electrons, positrons. Positrons are cool. Positrons are positively charged electrons. They can be created in like particle colliders and stuff, but they're not. I mean, you're not shooting out positrons from your body. Okay, positrons are neat though. They're like the antiparticle for electrons. Bless you. Bless you twice. All right. Neutrons. Neutrons are heavy. They come from the nucleus of an atom. Fast neutrons have anywhere between 5 and 20 as their radiation weighting factor. Average of 10. So if the radiation weighting factor for a neutron is 10, what's that saying?
It's 10 times more
Yeah.
damaging
Than
X-ray.
there you go. Okay, right. 10 times more harmful, right? So if I exposed you to 1 gray of X-rays or 1 gray of neutrons, and you had the choice between the two, right? You'd take the X-ray exposure, yeah? Because the neutrons are 10 times more harmful, Okay, that's the idea here when talking about the radiation weighting factor. You're saying this type of radiation is more harmful than X-rays. Here's how many times more harmful it is. Neutrons, 5 to 20 times more harmful. Alpha radiation is just 20 times more harmful. Okay. So yeah, you can ask how much harm is done by 4 milligray of alpha particles. Okay, and it's simple. You take 4 milligray, the number 4, and you multiply that by the number 20. And that's the radiation weighting factor for alpha radiation, and you get an answer 80. The unit that we're going to have here is just sieverts. Okay, millisieverts to be specific. So millisieverts, okay? Milli meaning 1/1000th, so 4 thousandths of a gray multiplied by the number 20 becomes 80, and the unit switches from gray to sievert, okay? This is telling you if you see a unit expressed in sieverts, you're being told here's how much harm was caused, 80 millisieverts worth of harm, okay? But yeah, it's much more simple for X-rays, right? Because the radiation weighting factor, and just to be clear, the radiation weighting factor is listed as a capital W with a subscript R, W sub R, okay? So if you see that, they're talking about the radiation weighting factor. But for X-rays, it's 1, okay? So the relationship between dose equivalent, the relationship between exposure and dose is a 1-to-1, right? We said that earlier, right? 1 gray of exposure is 1 gray of absorbed dose, okay? No matter what, okay? Now we're saying that for X-rays, 1 gray of X-ray absorbed dose equals 1 sievert of harm, okay? This is what's nice about X-rays is there's a nice 1-to-1 relationship with X-rays. We're comparing, for radiation weighting purposes, we're comparing X-rays to X-rays. So their radiation weighting factor remains 1, okay? So 1 gray of exposure is 1 gray of absorbed dose is 1 sievert of harm, as long as you're talking about X-rays, okay? If you're talking about any other type of radiation, the sievert, the amount of harm, is going to be more than the gray, because you're always multiplying by some positive number, either 5 to 20 or 20, if you're talking about neutrons or alpha particles. But anytime you're talking about X-rays, gamma rays, or beta particles or positrons, then the radiation weighting factor is 1, so absorbed dose is the harm. Okay, they're the same thing. 1 gray of exposure is approximately 1 gray of dose, is approximately 1 sievert of dose equivalent. Okay, but what you've told me up to this point is you've told me how much the person is exposed to. That's the air karma, or gray in the air, okay? From that, you can tell me the person absorbs 1 gray to the body, and from that, and knowing what type of radiation it is, you can tell me how much harm was caused. In X-rays, it's 1 sievert of harm. 1 gray of exposure in the air is 1 gray of dose, is 1 sievert of harm, of biologic harm. Good. So
but the sievert is the measure of harm.
Harm. Yeah. Sievert. Yeah. So you're not telling me much unless you tell me what type of radiation it is, and once you tell me what type of radiation it is, you get multiplied by one of these numbers, and that tells you relative harm. All it's telling you is relative harm. It's not saying like how much harm will happen. It's saying relative to some other type, right? So a good example would be, let me erase some of this. Right, so you're exposed to 5 milligray of X-rays, right? That's going to equal 5 sieverts of harm, okay? You're exposed to the same 5 milligrays, but this time of alpha radiation, right? Well, 5 times 20, 100. all that's telling me is relative harm, right? You're seeing relative harm. You're seeing, if it's x-rays, this is an amount of absorbed dose. Notice the amount is the same, right? Both patients, or both times, there was 5 milligray of radiation, okay? In this first example, it's 5 milligray of x-rays, and that comes out to be 5 sieverts. That's 5, not S. 5 sieverts of harm, okay? 5 milligray of alpha radiation is going to be 100 sieverts of harm. It's not telling you what's going to happen. It's just telling you that alpha radiation is going to cause more harm than X radiation. How much more harm? Just 20 times more harm. 20 times the amount of harm. So, you know, I could expose you to 1/20th of this in alpha particles and cause the same amount of harm as 5 milligray of X-rays. That's the idea, okay? It's just equating relative amounts of harm, not some objective amount. You're comparing one thing to another. It's a way to compare the apples to the oranges, right? Okay. So that was dose equivalent. So we've covered so far, we've covered exposure. That's measured above the body. From exposure generated above the body, you can infer how much was absorbed by the body. Knowing how much was absorbed by the body and knowing what type of radiation it was, then you can infer biologic harm. The next thing we need to know, so that was exposure, absorbed dose, and dose equivalent. The fourth one is effective dose, okay? Knowing those first three things, exposure, absorbed dose, and with the type of radiation, dose equivalent, okay? From those three things, you know a lot. You know how much harm is going to be caused, right? But you don't know the total amount of damage because you don't know the type of tissue that the body was, that was exposed, which type of tissue was exposed. You could have done that to, you know, the gonads versus the bone or skin, right? And those are going to be different amounts of actual harm caused. So effective dose, you have to, by the way, you have to get these four straight. This is a big part of our job, is understanding these 4 units and being able to talk about them, because the way we talk about the patient's dose is not the same way we talk about our dose, okay? We talk about us as being exposed and having a dose equivalent, okay? We talk about the patients as just having an absorbed dose, right? So, and those are different units. You learn that they're almost equivalent, but they're different units, okay? All right, the next thing to learn is effective dose, as I said. Effective dose takes into account everything we just talked about. How much exposure, how much absorbed, and what type of radiation giving you a dose equivalent. Knowing all of that, you add on what type of body tissue, okay? Okay, so this provides a measure of the radiosensitivity of a particular tissue or organ when compared to other tissues. The unit is again going to be the sievert, okay? So we'll say, you know, this patient receives some amount of sieverts of dose equivalent, and now taking into account their body tissue, we can say what the effective dose is in sieverts, okay? So to calculate the effective dose to an organ, the dose is multiplied by the weighting factor. W subscript T is the notation for tissue weighting factor, okay? Weight of tissue weighting factor. The relative sensitivity of the exposed tissue when compared to other tissues. And these are our numbers. So the nice thing is we're just given the numbers. We don't got to go figure them out. Now, notice these are all smaller than 1, okay? So whatever the exposure was, whatever the absorbed dose was in gray, when you calculate this out and get the answer, by the way, I gotta actually, real quick here, let me pause this.